The title of this talk is Memory Model. The objective of this talk is to put forward a memory model that would help us understand memory and memory-related problems. It is imperative for you to have viewed the video on memory classification before you go on viewing this video. I will conduct this talk in a question and answer format. First question: our knowledge of the mechanisms of speech and memory are at the same level. A, true, B, false. In 1874, Carl Wernicke put forward several useful speech models. You can see 4 of them in this figure from his monograph written in 1874. About 10 years later, in 1885, Lichtenstein created, based on Wernicke's models, a revised version which has become the basis for the speech models currently in use. The speech model, the one we are currently using, is not perfect. I have brought up the speech models at the beginning of this talk in order to highlight the shortcomings of our current memory model. I will do this by comparing where we are historically in the development of the perfect memory model in relation to where we are in the development of the perfect speech model. In order to make this comparison, I am granting us with 2 superpowers. One is time travel. The other one is knowing the future. So we are now in 2023. Using our time traveling ability, let's travel back to 1850 and forward to 2190. Now, using our other superpower, the ability to tell the future, let us say that in 2100 we will build the perfect speech model. I have now added an arrow to imply the historical trajectory of the speech models. As you can see, Wernicke's speech models in 1874 and Lichtenstein's speech model in 1885 were quite far from the perfect model. Now, again, using our ability to predict the future, I will say that in the year 2190, we will build the perfect memory model. The arrow I have just added indicates the historical trajectory of the memory model, just as the one below did for the speech model. But this time I have introduced our current memory model. Notice that the time spent from our current speech model to the projected completion of the perfect memory model is more or less the same as Wernicke's and Lichtenstein's speech models were when they were created. So the answer to this question is false. Next question. Instant recall and working memory have similar mechanism to store and retrieve memories. A, true, B, false. Regardless of the nature of an event, whether explicit memory forming event or an implicit memory forming event, the first step in memory making, instant recall and working memory has similar mechanism for recording and retrieving information. These mechanisms are housed at the unimoral or heteromoral association cerebral cortices. Most authors I have read believe that information instantly recalled must go to working memory before becoming long-term, explicit, or implicit memories. And again, be brought back to working memory so they can be expressed or displayed. So the answer to this question is true. Next question. Encoding autobiographical information is a function of the hippocampal formation. A true, B false. Encoding is defined as the transfer of working memory to long-term memory. The main structures involved in encoding explicit memory and maybe some of the types of implicit memories are the hippocampal formation and the cerebral cortex. The areas of the cerebral cortex involved in memory are the association areas. These areas are present in the lateral, mesial, and inferior surfaces of the cerebral hemispheres. For the benefit of clarity, I will use only the lateral surface of the brain to illustrate how encoding occurs. Here I have enlarged the lateral surface of the brain and superimposed the hippocampal formation in the corresponding area. I am now indicating the locations of the unimoral and heteromoral association areas for touch, vision, and hearing. Now I will use an example to hopefully make the explanation of encoding easily understood. In this frame, I have presented two people meeting for the first time. One person, the one with the big nose, is introducing himself to the other. And the other one, the one with the smile, is acknowledging the introduction. This introduction involved touch, shaking hands, hearing, and vision. So during this encounter, the one acknowledging the introduction will receive the information in each of the primary cortices, then pass it on to the unimoral and heteromoral association cortices where information will be analyzed. As part of this analysis, the information will be sent to the hippocampal formation, as depicted in this picture by the solid black lines and the smaller circles on the hippocampal formation. At the hippocampal formation, the newly arrived information is processed and encoded, which I have represented by the adding of magenta double-headed arrows between the little circles. Then, the encoded information is redistributed back to the cortical areas from where the information came from or to adjacent cortical areas. And in addition, the hippocampal formation sends a blueprint of this encoded information to the lateral aspect of the prefrontal cortex. I will now introduce the memory model to continue building it. As you can see in this frame, encoding, a function of hippocampal formation, as we have just heard, is represented by the green banner. Encoding transforms information previously presented in working memory into long-term recent explicit memory. So the answer to this question is true. Next question. Consolidation is needed to convert recent explicit memory into remote explicit memory. A true, B false. To recap what we have already learned about long-term explicit memory, information reaches the association sensory areas. From here, the information is sent to the hippocampal formation for encoding. And from the hippocampal formation, the encoded information is sent back to the corresponding association areas and to the laterodorsal prefrontal cortex. When a second similar event occurs, the information is processed in the same fashion. But now, again, under the influence of the hippocampal formation, intracortical connections start occurring between the different modalities of information, between the information in each modality, and between the prefrontal lobe and the different association areas involved. I have represented this process by thin yellow lines. Now comes the third similar experience, and the process is the same, making the intersensorial connections and the connections between the prefrontal cortex and the sensory area become more robust, as depicted by the yellow lines becoming thicker. Then the fourth similar experience comes with similar initial effects as the time before, that is, all interconnections become more robust. But in addition, the connection between the hippocampal formation and the sensory areas start to fade, as I have represented in this frame by the changing the solid black lines to interrupted lines. Comes the fifth similar experience, and the process has the same results. The intercortical connections become even more robust, but in addition, the hippocampal connections with the cortical areas disappear. And a to and fro connection between the prefrontal and association areas is established, as depicted in this figure by the addition of arrowheads in the yellow lines pointing to the prefrontal region. This two-way connection assures that further similar events are transmitted to the prefrontal cortex for temporal organization and future retrieval. At this point, no longer is the hippocampal formation needed to recall the experience. The explicit long-term recent memory has become remote. So again, I am reintroducing the memory model as we left it after the last question. The addition of the vertical line in the explicit long-term memory square, and now the word remote indicates that the transformation of recent memory to remote memory has occurred. A process that is called consolidation and requires hippocampal formation involvement. So the answer to this question is true. Next question. The role of the hippocampus in encoding implicit memory is uncertain. A true, B false. We have now gone back to the memory model figure. I want to call your attention to the implicit memory box. Encoding implicit memory, at least for most type of implicit memory, appears not to need hippocampal formation involvement. But it is uncertain if during an episode of anterograde amnesia, which is due to hippocampal formation dysfunction, a patient can be taught typing or to ride a bike. Hence, I have placed the green stripes in the encoding structure at this store to denote a degree of uncertainty as to the need of the hippocampal formation for encoding at least some type of implicit memories. So the answer to this question is true. Next question. Explicit memory has only one mechanism to retrieve memories. A, true, B, false. So again, I have now introduced the memory model as we left it after the last question. I want to call your attention to the explicit memory box. Retrieval of recent explicit memories, the transfer of recent explicit memory to working memory needs hippocampal formation involvement. Retrieval of remote explicit memory does not. Retrieval of explicit remote memory is solely a cerebral cortical function. Retrieval of implicit memory does not need hippocampal involvement either. So the answer to this question is false. Next question. Repetition is the only mechanism that contributes to consolidation. A, true, B, false. Meeting John is less memorable than meeting a vampire, despite both activating the same cortical areas. This is because of emotion and fear encourage memory consolidation. This is so due to the activation of the Papez circuit and probably in the case of fear, activation of the amygdala. In this frame, I have illustrated the two-way connection between the prefrontal cortex and the amygdala. So the answer to this question is false. Thank you very much for your attention.